So in this example, we're going to locate the centroid of the given area element, or the given area. So the first thing we're going to do to find the centroid, so we're looking for x bar and y bar for this given area, is we're going to first define what is our differential element. All right. So to define our differential element, right, we're going to take a small section cut, or small element, out of our differential element, out of our area, and if we take that small element out, alright, that element will have a very thin width. We'll call that width dx, and then the height of that element we define as being just equal to y. Alright, now for our differential element, we also want to define what is the centroid of our differential element. So the centroid of our differential element will occur, so this is our x tilde and our y tilde, this will occur at the x coordinate of our centroid of this area will occur at just the location in x, and then our y tilde would be equal to the value of y of our element divided by 2, or the height of our element divided by 2, which would be equal to y over 2. Right? And then the last thing we want to define for our differential element is what is our differential area. So our differential area in this case would be equal to the width times the height. So it would be equal to the width, which is, or it would be equal to the height, which is equal to y, and then times the width, which is equal to dx. So now that we have our differential element defined, our second step would be to determine what formulas we need to use. So it's our formulas for x bar and y bar. So for x bar, our formula is equal to x tilde dA divided by dA, the integral of dA. Alright. And then for y bar, it would be equal to our integral of y tilde dA divided by the integral of x, integral of dA. Oops. Right. So after we determine our formulas, we just need to evaluate our integrals. Right. So we just have 1, 2, 3, and then this integral in the denominator of both of these is a shared integral. So we really only have 3 integrals we need to evaluate. So the first integral, or we'll solve for x bar first. So for x bar, we will have the integral of x tilde dA. So x tilde we defined it from our differential element as just being equal to x, and we defined dA as being equal to y dx. Now we know that from the problem that y is also equal to x squared, so we can rewrite this all in terms of x. So we can write it as being equal to y x squared, dA is equal to x squared dx. So that's what we're going to plug in here. Alright, and then the bounds of this area in x goes from 0 meters to 1 meter. So we're going to use that for our bounds of our integral. And then the denominator of our integral will be just dA, so it'll just be x squared dx from 0 meters to 1 meter. Okay, so if we just evaluate those integrals, you would get, it'd be 0 meter, 1 meter, and then we would have x cubed dx divided by 0 meters, 1 meter, x squared dx. If we evaluate those, we would get x to the 4th over 4 divided by x cubed over 3 from 1 meter to 0 meters for both the top and the bottom. If we did that, we would end up getting 0.25 meters to the 4th minus 0 meters to the 4th divided by 1/3 meters to the 4th minus 0 meters to the 4th. So that we end up getting is 0 x bar would be equal to 0.75 meters. Right. And then we can do the same integral for y bar. So if we do that, we would, or not do the same integral, we have to do the integral for y bar, or use the formula for y bar. So that would be equal to the integral of y tilde, which we know is equal to y tilde, we know is equal to y over 2. And we know that y is equal to x squared, so we can plug in x squared over 2 for y tilde. And then dA we know is equal to x squared dx. And we know that the bounds of dx go from 0 meters to 1 meter. And we know that our integral on the bottom is going to be just the integral for dA, which we know goes from 0 meters to 1 meter, x squared dx. Alright, since we already solved for that integral, we already know that this integral is the same, so we can just say that it's going to be equal to 1/3 meters to the 4th. Alright, meters to the, sorry, this should be meters cubed here. Alright, so if we evaluate this integral here, what we end up getting is we would get the integral from 0 meters to 1 meter of x to the 4th over 2 dx, and then we would get if we integrated this, we would get x to the x to the 5th over 10 from 1 meter to 0 meters over 1/3 meter cubed. And then if we plugged all this in, this would end up just being 1/10 meters to the 5th minus 0 meters over 1/3 meters cubed. Alright, and then we know y bar from that would be equal to 0.30 meters. Alright, I know that if you notice here that you should get meters squared, but the reason we get meters squared is because we have y is equal to 2 x squared, so it gives us an extra meter. Anyhow, so for these types of integrals, if you get an extra meter or something, don't worry about it. It's just after you make a substitution for the other variable, your units might not agree, but as long as you do your substitutions correctly, just write the unit that it should be. So for centroids, everything should be in terms of length. Alright, so just to summarize what we did is from our problem statement, we defined our differential element. We defined it in this example in the vertical direction, but you could have defined it along this direction as well. Nothing wrong with that. And then after that, we used our formulas for x bar and y bar, and we plugged in our x tilde, y tilde, and our definition of our differential area from our differential elements. And then after we did that, we just solved our integrals. All right. So that's it. So that's the general procedure for determining the centroid of a continuous function using integration.